Hello everyone. Today is the 61st day of Leetcode 75 challenge. Let's begin with the 61st question. Question 198, House Robber. The level of the problem is medium. I will request you to read the question beforehand as I will deep dive into the PPT and explain it in simpler way. You are given an integer array nums, okay, where nums of I represents amount of money in the ith house. Okay, fine. So you have been given an integer array. Great. And they are saying that nums of I consist of a number something like this or whatever. This number represents the amount of money which is present in this particular house. Okay, let this be house 2, house 3, house 4, this way. Okay, you cannot rob two adjacent houses because they have connected security systems. At each house you must decide whether to rob it or skip it. If you rob a house you must skip the next one. So basically, I hope you understood the wordings, but let me explain it again. Suppose if you have robbed this house, you cannot rob this one. Okay, because they have some kind of a security that if you rob this house and you try to rob this house, the alarm will budge, right? Rather, if you rob this house, you can rob this particular house, then this particular house. Okay, if you don't rob this house, then if you rob this house you cannot rob this one, then you have to rob this one and you cannot rob this one. Okay, this is the way you have to follow. The goal is to rob houses such that the total amount of money is maximized without robbing two adjacent houses. So you have to maximize the money. That's all. Return the maximum amount of money you can rob without alerting the police. Okay. So basically, you have to follow this structure, and the money which you get has to be maximum. Okay. Of whatever ways you take. So the constraints of the problems are the nums length could be from 1 to 100, and the value of the nums of I could be from 0 to 400. So I hope you understood the problem explanation. Let's move to the next slide. Now let's understand the input output explanation. So if you can see this particular house or this particular array, there are one, two, three, one. Okay, if you think of starting to rob from this particular house, you cannot rob this house, right? Then you can rob this house, then you cannot rob this house. Sum comes out to be 4. Okay, let me draw this as an array. So okay, so you started that way, right? If you started off not taking this particular house, you took this house, you cannot take this house, then you took this house. Sum comes out to be 3. Okay, again, this was the most efficient way we took, right? What happens if a person thinks of taking this house, then directly this house, or not this house actually, the last house, right? It's 2. So there could be multiple ways, but the most efficient and the maximum one which we can get is from this particular scenario. Okay, that is why the output here is 4. Now at example 2, in this particular house, let's take this one. Okay, so answer is 12, right? If a person robs this particular house, then this particular house, then this particular house, the total sum is what? 9, 10, 11, 12, right? Great. Let's try some other combinations. Okay, if the person starts from here directly and goes in this particular one, then goes out, right? Sum is 10. So this way you could try much more possible combinations. You could say it's not a combination exactly, but yeah, the number of patterns if you can take. So this is the only one which will give you the maximum answer here in this particular scenario. Okay, I hope you understood the input output explanation. Let's move to the next slide. To understand what problem is asking, we should build up an intuition to the problem. Okay, so let's do that by understanding the goal. Okay, so here if you could see, we are given an integer array nums, where nums of I represents the amount of money the ith house has. Okay, and we can either rob or skip a particular house. However, if you rob two adjacent house, the security system will trigger the alarm. So we have this particular scenario in our mind, right? The goal is to maximize the total money we can rob without robbing the two adjacent houses. Okay, so we have the complete understanding of this. Now what could be the brute force for this particular solution? A brute force approach would try all combinations of robbing and skipping houses, but that leads to an exponential time. So how exponential? Because if you could see, uh, suppose this is a random array. Okay, if your I is standing here, this I has two options for this particular scenario, right? For this particular house, either it can take it or it can not take it or skip it, right? Basically the one thing. So each has two options, therefore the time complexity for this particular for the brute force comes out to be 2 to the power n, right? So we have to optimize this to 2 to the power n, right? That is our goal now. Now let's try to visualize the process. So suppose we have this scenario with us, right? And we are starting with the index 0. Let me write the indexes also. Okay. So if you're standing with the 0 index, suppose you have this array here, okay, and you're starting with a 0. So you have two options. Either you could take it or you could skip it. For T means take, S means skip. Okay, just go that way. So if you take it, what will happen? If you take the particular scenario or the particular value, the value will be 1. Okay, and the index will be 1 also, because here we were starting at index 0, right? Now we have the index 1 here. Now again, from here you have two options, either you could take or you could skip it, right? If you think of taking it, then the sum, then what will happen? Just keep in mind, if you take, if you have taken the previous one, you could only do I plus 2, right? Common sense, because if you take this particular one, you cannot take the 2 value, you have to go to 3. To going to 3, 5 was 0, then you have to add 2 to it, then it becomes 2. And when it becomes 2, you are standing at a particular index 2 with the value 3, right? I hope you are getting that particular thing. So here, when you take, it has to be I plus 2 each time. Okay, so if that happens, if that happens sorry, I plus 2, not I plus 1. I wrote I plus. Let me write it with a different pen so it's more clear. Okay, so I've written it here. If we are taking it, it's I plus 2. So if it's I plus 2, so the value was 1. So 1 plus 3 becomes 4, and the index which we are standing is at 2. Okay, again, if we go recursively, again, if we take and skip is here, right? If we try to take again, right, we have to do I plus 2. From here, I plus 2, if you do I plus 2, it goes out of bound, right? That means you have to return from here. Okay, so if you return from here, then we'll come to this particular scenario, which stands for the skip. If we skip, which means that you are standing here, now you are skipping it. That means in the next step, you won't be taking this value, right? So the sum will be 4, but the index will be 3. Okay, because you came here, but you didn't took the particular value, right? Then again, you have take and skip. Taking is not possible out of bound OB. Okay, but if you try to just skip also, that is also not possible. It will also become out of bound, right? So it has the value 4 from here, so it will return the 4 only. Okay, great. Now let's take this particular scenario. Now here we are standing at this particular 0 index. The next index will be 1, right? So if you try to skip, right, if you try to skip, the sum remains 1, the index increases to 2, right? Because you were standing here, right? First you started from here, 0th index. From when you took the value, the sum become 1, right? And the index become 1, right? Now from here, you didn't took the first index value, but you arrived at that, but you were standing at that index. Understand? Now from here, you tried thought of skipping this value 2, not and not taking it. Then you came to this particular index, right? Index 2. Now from here, you have two options, either you could skip it or you could take it. So if you try to take it from here, if you try to take the value, what will happen? You were standing at 2, right? So you took the value, so it became what? It became 4, right? And index became 3, correct? Again, you have two options, skip it or take it. If you try to take, it will be from index 3. Next will be index 3 for it, right? But that is not possible, because it will be n plus 4. n plus 2, right? So it will be 4. Sorry, I have written 3 here, it should be 4, because you have taken the value. So it is already out of bound, so you will just return from here. Okay. Okay, so from here if you try to skip means just doing n plus 1, I plus 1, right? So that is also not possible, out of bound. Okay, so this will return 4 from here, whatever the value it got. Now if from here if you try to skip, right, that means that it's still 1 and you're standing at index 3. Now you have two options, right? Again, take and skip. So if you try to take, it will be an out of bound scenario, and here also it will be out of bound scenario. Both the cases will be true. Okay, so I hope you understood this particular scenario. Again, I will just take the skip one and then we will move ahead. So from here, if you could see, if you skip this zeroth index, the value sum will be 0 and the index would be 1, right? Again, you have options here, which is take and skip, right? So this will go again. So from here, if you could observe this particular part and this particular part has this same value as the sum, right? Is there any more? Yeah. If you could see, this also gives the same sum, right? Anything else? Okay, there would be more scenarios, but we have to make this quizzes. It will take a lot of time to do that. So yeah, since from here we can see that we have repetitive values, repeating decision pattern makes it a classic dynamic programming one, right? Because here we could see repetitive values 4 comma 2, 4 comma 3, 4 comma 4. We have already getting the same sum again and again, so why would we go for further investigations of the particular scenario, right? So therefore, I hope you understood this recursion tree, how the recursion works here in the scenario, and how it is a dynamic programming solution, because the problems are repeating again and again. You have to remove that particular thing. So now, how we can simulate this particular thing, right? We have to focus on that now. So to if you go with the points before that, we know that we have to take the length of you know uh, the nums which is given to us, right? We have to create a dp, right? A dp size would be how much? It would be n plus 1, one base indexing, right? Then we will create a function. What those this function will have? This function will have, and one more thing. In this particular scenario, I have explained you from you know from I equals to 0, but in our code, what I have written, I have started from n minus 1, right? So this also works the same way, right? Just it starts from the n. Okay, so we will pass n minus 1 index, or to be much more clear, if you want to just say 2, 3, 4, 5, 6. So I will take 6, or I won't take 6, right? If I take 6, I won't take this particular value, and then we will take this value, right? This is the same scenario. If you could see, we started from 0. Instead of that, we could have started from n minus 1. Then it could be n minus 2 here, then n minus 3, n minus 4. So this way it might have been moving. Okay, so yeah, so in that function we will pass this particular index, the important one. Then we would have to pass the nums array also, so check for it, the dp array, and the n, the size of the particular array. Okay, and after that, in this function, we will place a condition. If index is 0, we only rob the first house and return nums of 0. Why this? Because if you're starting from n minus 1 and you came, however, in whatever direction you came to index 0, you will of course take this value, right? And just you will return it from there, right? If index becomes less than 0, that means that it was this way, and it became a scenario that you were standing this and you took this value, so you cannot take this value, right? So what you will do, you will do n minus 2, and because of which you will come out of bound, or index becomes less than 0, right? So what you will do, you will know house to rob, you will just return 0 from there, right? So if the result is already computed, which means that if you dp if of index, if it is not equals to minus 1, that means that for this particular index we have calculated the sum. So we will just return from there, we won't be going much more further, right? Now what will be the function look like? Main function, right? Recursion take. If we try to take, so of course nums of current index, we have taken this, right? If we have taken this, what will happen? Num fun of n minus 2, right? Because you're skipping the next value. And if you don't take it, right, what will happen? Fun of n minus 1. Simply we will just move to the next index because you're not taking it, right? So we won't be adding anything. Now, for the value, when we'll try to return, it should be max of the take or n take. Okay, that's clear, I guess. Then at the end, when everything is done, we'll just return the val, or instead of val, dp of index. Okay, at that particular index, what is the maximum sum you're getting from take or not take case. Okay, so what we figured out is that a plain recursive solution would recompute the same sub problems multiple times, leading to an exponential time, which is 2 to the power n. And with memoization, we store already computed results in a dp, reducing the time complexity. Space complexity is also linear due to the recursion stack and memoization array. Okay, so I hope you understood the intuition. Let's move to the next slide. Now, since we got the intuition of the problem, let's look into the approach how we're gonna solve it. It goes the simple way. In the main base function which is given to us, which is named as raw. Here, in the main function raw, we create a dp array of size n and initialize it with n minus 1. It will be as dp of dp equals to minus 1 into n plus 1. Okay, one base indexing. Why we do this? This array stores the maximum money that can be robbed up to each house and helps avoid redundant computation for overlapping sub problems. Okay, and after that we will handle the base case in the function fun, which we will create for the recursion. In that, if index is equals to 0, that means we have already reached the 0th index and we have to take that value. We don't have any option. We will just return nums of 0 from there. If by chance, if index is less than 0, which means that we were standing at index 1 and we have taken that value and we cannot take index of 0. So we have to go n minus 2, which becomes out of bound. In that scenario, what we will do? We just return 0, right? Because we have not taken any value from there. Okay, because it is what it is written here. Okay, in step 3, it is the main recursive call, which we already talked about the base cases. Now there comes the memoization, right? In memoization, we will just check that if dp of index, if it is not equals to minus 1, which means that if dp of 2 is not equals to minus 1, which means that for index 2 we have already calculated the sum up till that particular scenario, up to that particular index, you could say. Okay, and after that we will have the take case. If we write it in the proper manner, it will look like, if I take case, it will be nums of I plus function of n minus 2, comma nums array, comma dp, comma n. Okay, and if you try to get the case of n take, it will be fun n minus 1 nums dp and m. Okay, and then what we will do? We will do dp of index equals to max of take and not take, and at the end we'll just return dp of n. Okay, because this avoids decomputation and builds a solution using previously solved problems. So this will be our main recursive function. Okay, and this will be our base cases, and the final output will be when the dp of n is written from the rob function, it comes back to the from the fun function, it comes back to the base function rob, where we have already called the function fun. Okay, from here our answer will get returned. So I hope you understood the approach explanation. Now let's move to the next slide. The code is the exact copy of the approach discussed. Let's understand it line by line. So if you could see, we have taken the length of the nums array, we have initialized the dp on one base indexing. Okay, and we have called the function here. Now this is our base cases. If index is 0, return the nums of 0, otherwise return 0 if the index goes less than 0. We check for the recomputed values here, and we call the take and not take function, take the maximum and just return the dp of index. Okay, My bad, I explained here mistakenly dp of n, it should be dp of index. My bad. Okay. Now time complexity in the recursion, it was 2 to the power n, right? Because for each we were taking the both the conditions. But here, since we have avoided that, time complexity boils down to O of n, because we are doing it in only one iteration kind of a thing. You could take it that way. And space complexity is taken O of 1 because the DP array which we have created is of size n. Okay, so I hope you understood the code explanation. Let's move to the next slide. Now, since we have the understanding of the code, let's look at the dry run of the example. And also, I have brought down the code for our understanding here. Okay, so this is the array, this is the value, this is the output. So I will just create a DP array n plus 1, right? N is 5 here. Okay, okay, so I have created a DP array here. Okay, so first task is done. Now we call the array. Now we're starting from the end, right? 27931. Okay, so this is 0, this is 1, this is 2, this is 3, this is 4. N is 5, right? N minus 1 becomes what? 4. That is a common thing. Okay, so we are standing it here, and we are taking a decision that whether we should take that value or not, right? Right now the index, let me represent this index. The index is not 0, neither it is less than 0, and dp of index is also equals to 1. So we will do the take case, and if we do the take case, our sum becomes, okay, let t be the take case, and this will be the skip case. Okay, so if you do that particular thing, what will happen? Our sum becomes 1, and index become 2 is n minus 2. N minus 2 means we come to second index, right? Great. Again we go back, because this thing is called index is not 0, neither index is less than 0, and also dp of index of minus 1, it is also equals to minus 1, right? So we come to the take case again. Here we were standing in this part, right? So for the value for that part was 9. So the part 9 plus 1 gives me 10, and the index becomes 0 because we do n minus 2 from there. Okay, great. Or index minus 2 from there. Again we go back, we check. Okay, right now our index is equals to 0, right? Because from here we came to here. So this returns the nums of 0 from here, right? So nums of 0 is 2. So sum becomes 2. I'm just writing it a shortcut case here, right? And we just return it from here. Okay, we return it from here. Okay, now from here we came to this part. It was 10, and we were standing at 0, right? And from here, if we try to skip this, we try to do index minus 1, right? So that becomes out of bound, right? So this returns, so this becomes index minus 1, right? Becomes negative number. So index minus 1 is we just return 0 from here. Okay, so then you come here, then and dp of 0 maximum is what? 12 or 0? 12, right? So our sum here becomes 12. Okay, then we go back again, then here we try to do the skip case, right? So for that particular scenario, we were standing at index 2, right? And come here, yeah, we come here with index 1, and our sum still remains the 1, right? Okay, so similarly we can do the complete recursion calls, right? And at the end, since we started from here, so at the end we will have the all the values present here, and we will return dp of 0 when we reach the particular end. When the array here, when this index exactly comes here at the index 0, we will be having 12th value, and we will just return 12 from there. Okay, so I will request you to do the complete dry run by yourself here, because the video will become very long if I do this particular dry run. But I think you have got the understanding of the dry run, how it will go ahead. right? And also we have already done the recursion part, so it's just the same. You just have to update the DP value in this particular scenario. Okay. So if you have any doubts or confusion about the solution we arrived at and how we arrived at it, I would suggest going back and understanding the intuition, the approach, the code, and after that do a dry run by yourself on 2 3 examples. I'm pretty sure you will understand both the solution and the thought process behind it. So let's move to the next slide. Now since we are familiar with the problem and the solution, let's move to the lead code and code the solution. So let's start by taking the length of the nums array. Let's create a DP array. Okay, and I just will return from here. So here we will have def function with index, nums, dp, and n. Okay, if the index becomes 0, we just return nums of 0, nums of 0, or if index become less than 0, we just return 0. If dp of index is equals not equals to -1, then we return the dp of index from there itself. Then we have the take case, which is basically nums of the index plus fun function. We took the value, right, so it will be -2, then it will be nums, and it will be dp, and it will be n. Okay, if you don't take the value, it will be just self dot fun index -1. We're not adding any values, so it's okay. And then okay, and then we will just return when we reach the base case index of 0, then we return. Okay, so what is the particular index value is. Okay, let's try submitting for the base test cases. Okay, I forgot to write 0 here. Okay, I forgot to write self also. Let's try again for the sample base cases. Okay, I just forgot to take the maximum here, dp of index. That's the most important part. I forgot to do that. Okay, let's try again. Okay, let's finally submit the solution. So we have successfully submitted our solution here. Now the code of the problem is available in my GitHub repository. You can find the link in the description. Thank you everyone.